Okay, this is continuing experiments in the transference of electric power. Today we're having a look at a similar experiment as before. I'll just pan around so we can see. There's the experiment, there's a TMT transmitter, TMT receiver connected by a single wire with a load-in as before. That's now a 60 watt 4-bulb load, and with various measurement equipment attached, a high voltage probe attached at the center and a current probe, Tektronix current probe connected in the middle. At the far end, we'll have a look at that in a minute, we've got the usual bulb load attached to the receiver. Now this time we're going to have a look at driving this system with a spark gap generator, which actually makes a reasonable difference. Before we were looking at driving this with a vacuum tube, the 811A vacuum tube generator, and we're going to make some comparisons and look at the difference between the characteristics when you drive actually the same transmission system, the same TMT transmission systems, but with a different generator. Now the spark gap generator is obviously considerably different to the vacuum tube generator. The vacuum tube generator was being used as a linear oscillator, so it was also tunable to single frequency, and we were effectively applying a sine wave across the whole of the system, whereas now we're using the spark gap generator, we're now talking about bursts of energy. So oscillating bursts, oscillating currents, and the range of frequencies generated in the spark gap is much, much wider. So we're now looking at a broadband spectrum that we're going to use to power the transference experiment. And when I say broadband, it really is all the way from quite low frequencies, down in the hundreds of hertz, right up to very high frequencies, up into the hundreds of megahertz and even beyond. So in a way we are exciting the circuit with simultaneously a wide range of frequencies. That's what makes it a broadband generator, generating oscillating currents. So the high voltage supply is obviously providing the tension to the spark gaps. We have a tank capacitor in the circuit. I'll show those in a minute, and obviously the four series spark gaps that we've looked at before in other pages on the website. So if we take a look at the setup of the experiment, what we have here, there's the high voltage supply, and we're using two of the microwave oven transformers in series. So that's going to give us a total open circuit voltage of about 6 kilovolts, which is more than enough to drive this series spark gap. So the output of the transformers are connected across the spark gap. Here we have a series spark gap that works its way down, adjustable on this side, so we can adjust the size of the gap, and that allows us to tune the spark for the most optimum characteristics for the impedance that we're driving. So then we come in parallel with the spark gap, we've got the actual experiment. We're using the tuning circuit again as in the previous experiments, but this time we're using more of the input features. So from this side we come out of the spark gap, we go through a 5 amp RF ammeter, that's a Western 425 thermocouple meter, so it measures the average, the RMS of the RF current, which is quite important to do when it's a very broadband spectrum like this. That comes out, it goes into, this is the first half of the serial tank capacitor. So in other words, there are 4 capacitors here, doorknob capacitors. They are 4.7 nanofarads each, and we've got 2 in series and then 2 banks in parallel. So that still equates to a 4.7 nanofarad total capacitance. Obviously we've increased its voltage rating. These are about 3.5 kilovolts. 2 in series is going to make 7 kilovolts, which is enough for our generator. Those are fed here. Now at the moment we've got this copper shunt across here. So literally the energy comes here, down and out and down into the coil. The 1B22 vacuum spark gaps, they are for actually not going to be used in this experiment. They have a trigger voltage of about somewhere around about 2.5 kilovolts, but their impedance is quite high, so they will considerably reduce the current, the oscillating currents in the system, which is why we have a shunt in this experiment here. So then that's fed down to the primary. Out of the primary, again on the other side, through the shunt, another 4.7 nanofarad set of capacitor bank here, out the lead, through a Tektronix current probe, although we're not seeing that at the moment, and then back to the spark gap. And as before, we are measuring the high voltage potential actually across the copper strap primary. We're using a high voltage probe which is connected to a frequency meter, which is also connected to the purple trace on the oscilloscope. And actually the purple trace is connected to this side of the experiment. So if we were adding more traces here, then we would also be able to monitor the voltage at the primary. But in this experiment, we're going to look predominantly at the voltage in the single wire and also the oscillating currents flowing in the single wire. Normal power incoming to the transformers, as usual, and that's about all the setup for this part. I'll just give it a little try just to make sure everything's set up correctly. Here we are, running about 300 watts in as before. Spark gaps are nice and steady and stable. We're reading about 4 amps RF current in the primary circuit, and we can see obviously this is showing the burst waveform that we get. So this will be, the spark will be operating at 100 Hertz. That's the positive and negative cycle of the line frequency, which is 50 Hertz. And then we're triggering at the beginning of the start of the discharge. So this represents a discharge burst that flows around the primary circuit. Obviously we've got multiple frequencies there. That's the frequency of the oscillation in the primary and also frequency of the oscillation in the secondary. Okay. The oscilloscope is left to pause when it triggers, so we see the last waveform that it measured was actually left on the screen. I'm just showing that again, run and stop. Okay, so that's the setup of the system. What we're going to do is just going to have a look at again how Z11, the small signal AC impedance of the circuit, looks from the spark gaps through the system. So in other words, what the impedance of the circuit looks from the generator's perspective. And that will be obviously from the points of the spark gap, so from here. So how does the circuit look looking this way from this point forwards into the circuit? Now Because this is a spark gap system, we are looking to, and we're working with oscillating bursts of current, we're looking to drive this or tune it somewhat differently to the way we were doing the vacuum generator with the 811As. What we want to do here to get maximum transfer of energy between the primary and the secondary in the TMT, it is best to get the resonant frequency of the primary circuit equal, where possible, to the resonant frequency of the secondary circuit. Once again, we've got our tuning capacitor in parallel with the primary. This is a 1200 picofarad 4 kilovolt vacuum variable capacitor. We are obviously we're not running this up full, so that's enough in terms of the breakdown voltage. Ideally, we're running, well, we can see what we're running here. So this will allow us to look at what happens when we tune. This works exactly in the same way as the previous part we did in the transference of electric power. And we can wind that all the way closed, and we can wind that fully open all the way up to, that's about 20 picofarads fully open, and when we close it, it's around about 1200 picofarads fully closed, and that's in parallel with the two-turn copper primary strap. So what we're going to look at next is the effect of tuning this and find out what kind of impact that has on the circuit. Obviously, we've got a somewhat different input circuit now, and that's going to make quite a bit of difference to what our AC characteristics look like in comparison to what we did with the vacuum tube. Okay, so just before we go on, we'll show just the overall operation of the circuit, so we can see all of the pieces running together. So at the moment we're having a look at the normal instrument rack that we have. I did mention some of those items before, but we also have the frequency counter here that's connected to the high voltage probe that's connected across the input to the primary. So there we get, this is set for a very high averaging, so it will give us a more clear indication of a central oscillating frequency. I mean, there are many frequencies going on in this system, but we want to try and get an idea of what the central frequency in that energy distribution, what that will look like. And if we put this universal counter onto averages, it's on currently 10 to the 6 averages, then we'll be able to get a better view of that. The oscilloscope shows the purple trace is the voltage at the centre of the single wire between the two TMTs, and the red trace is the current in the single wire as measured by the Tektronix probe. So what we're going to do is I'm going to start this running, and then I'm going to pan it around so we can have a look at what's happening in the circuit before we go any further. So using the remote control, I'll just start it up. We can see the burst waveforms on the oscilloscope. We're around about 300 watts, which is what we were running, the same power we were running the vacuum tube oscillator at, or at least the input power to the high voltage transformers. And we can see here we are measuring 2.4 megahertz, and it's quite stable. So that gives us an idea of what that central, the strongest central resonant point for the current setup of the system. If I were to just reduce those averages, you're going to see it jumping around a lot more. So a big range of frequencies going on in there. Put that back. Okay, so letting the spark gaps run, we're just going to pan around, have a look at what's going on in the experiment, and we can see there that we've got the central load is lit. It's about 2/3 lit. If I were to increase the power slightly, 400 watts, you can hear the spark gap becoming more aggressive. There's 500 watts, and now they're almost fully lit. Back down to 400. Back down to 300 watts. And at 300 watts again, we have a current as measured by this Western 425 RF ammeter of about 114 milliamps. If I go up again to 500 watts, that's gone up to about 160. Back at 300 watts, about 145 milliamps in the single wire, and also the burst waveforms on your oscilloscope showing actually quite high burst currents going on. That meter, Tektronix meter, is set to 50 amps per division. So we can see right at the beginning okay, we just take another look at the oscilloscope. We can see the red trace, which is the current in the single wire. We're running just around about 300 watts, but the burst current at the beginning is quite high. Now that's calibrated at 50 amps per division, and that implies that some of those currents in the single wire are quite large. So just again, back to the experiment, just see how it all looks. Now at the end, the bulbs in the receiver load are not currently lit. So in other words, we are back in that situation where there is energy being coupled from the primary to the secondary in the transmitter, and that is being dissipated in the load in the single wire. That was very much a similar situation we had before, when with the vacuum tube generator, when we did not have the right tune between the transmitter and the receiver. So they were slightly out, or not exactly within the same band, and we get that power dissipated in the central load and in the single wire. And we're going to have a more detailed look at that later. Coming back round, and the first thing to do before we do more on the experiment itself is to have a look at the small signal AC analysis from the perspective of the generator. Okay, now we're looking at the Z11, the small signal AC input impedance, and what we've done is just to show what it looks like in the experiment. So we've unplugged the high voltage probe, and we've put the vector network analyzer in its place, and that is connected now directly to the output of the spark gap. So we're seeing everything from the output of the spark gap through the TMTs and into the experiment. Now at the moment I've got everything connected, so once as before I'm just going to remove the receiver so we can have a look at the results. We are dynamically, actually let me just start sweeping. So we go continuous sweep. Okay, so now we're taking scans, and I have got the primary tuning capacitor fully open. So it's around about 20 picofarads. That's fully wound open. And what we actually see now is actually very similar to what we had before, although we have an additional resonant circuit in here. There are now, instead of the situation with the vacuum tube generator in part 1 of Transference of Electric Power, where we had, when we were just measuring the transmitter, we had the secondary circuit, the resonant secondary circuit. We had the resonant primary circuit formed by the 2 turns of the copper strap, which represents the inductive part, predominantly inductive part of the primary, in parallel with the high voltage tuning capacitor, and that forms the second resonant circuit. But now we are looking at a third resonant circuit as well. So in other words, we have the series tank capacitors, the 4.7 nanofarad tank capacitors, either side in series with the primary, and it's in series with that primary resonant circuit. So obviously the overall effect from an impedance point of view is when those 4.7 nanofarad tanks are in series, effectively we're looking at a 2.35 or round about 2.3, 2.4 nanofarad series capacitance, which is connected to the parallel resonance circuit of the primary. So in other words, we've got now 3 resonant circuits interacting here in this system. Of course, when we connect the receiver, then we're adding the receiver, the 2 resonant circuits in the receiver as well. So the secondary of the TMT receiver and also its primary. At the moment we've got 3 resonant circuits. So we're just dealing with the transmitter part. I've got a small wire out of the bottom of the secondary of the TMT transmitter, which is basically just acting to lower the impedance and to keep that measurement within a quarter wave measurement for the transmitter TMT. So if we look at the results now, we can see these 3 distinct phase changes here. So as before, this frequency here, that actually comes from, if we just have a look at what frequency that's actually at, take it right down there, it's obviously almost very low impedance, series resonance at 1.22 megahertz, and that is what is predominantly about those series tank capacitors. If I was to take out one of those series tanks, then we would see that change. So if I first of all disconnect, and now I've taken out one of those series capacitors, so in effect the capacitance has gone up, we see that this has now moved down because the tank capacitor has increased. Our tank capacitor is now 4.7 around about 4.7 nanofarads rather than the 2.3 that we had before. And so we would expect that series resonance to drop as that capacitance goes up. As then this second peak, or the second phase change here, is as we had before for the secondary coil. So that represents the TNT transmitter secondary, and up here again we've got that very similar. We've got that parallel resonant circuit formed with the primary and its vacuum tube tuning capacitor associated with obviously its impedance peak and its phase change. I'm just going to plug back in the tank. Back in the tank capacitor, we can see that first resonance here has gone up again because the capacitance dropped just to there. And obviously we've still got harmonics. This is harmonics of the TNT transmitter secondary, much as we saw before. So if I now start to wind in the capacitor, so I'm increasing the capacitance slowly, we will see, okay, if we look at the far end, we start to see that phase change, which is part of the parallel resonant circuit of the primary, starting to come down, starting to collapse. Impedance is moving down here. Obviously it's about to interact with, there's an interaction with one of the harmonics of the secondary, as we saw before. Keep reducing. We're going into there's interaction with another harmonic. Impedance is really rising up again as it did before. Not much change here, of course. Just pause it there for a second just to go over that again. But in this particular flat coil arrangement, as we spoke of before, the wire length in quarter wave mode here, the wire length very much determines this phase transition, and that's why that is not changing and that phase transition is not moving. Also the tank circuit resonating primarily with the primary, that is also not really changing at this time. So we're going to carry on reducing, carry on increasing the primary tuning capacitor. Just going to get interaction there again with the second harmonic, second odd harmonic of the primary, of the secondary, sorry. Keep coming down, keep coming down. We're seeing similar type of results as before. So now the impedance peak from the secondary start to rise up in a similar way as the primary and the secondary start to interact. So we saw this before in part 1 of the transference. This hasn't changed, and it wouldn't change because the tank capacitor isn't being adjusted. In. We're coming down to around about 600 picofarads. We'll be coming into that optimum balance point soon, where the impedances are matched. Around about there. So there, that would be around about just around about 800 picofarads. They're about the balance point. So now you can very clearly see the three phase transitions that are taking place. And also this big peak here that has entered at the top, which is representative of the third resonant circuit. So there's such a spread there. So we've got a phase change down here at, let's have a look where that was. It's a series resonance. The impedance there is very low, so only about 1.26 ohms at the bottom, and at, let's just move those a little bit so we can see them, 1.11 megahertz. So it has dropped very slightly as a result of the pressure of the primary starting to push on those other resonant circuits as they come in close resonance together. So we're going to keep bringing it down. Keep bringing it down. We've gone through that optimum balance point. Still not fully closed. Everything's pushing downwards. So there we are, wound fully in. So we can see everything again has compressed up at this end. Very dominant impedance at the lower of the resonant frequencies, and the upper resonant frequency of the transmitter TMT is very much suppressed now. This has moved in very slightly, and the tank circuit resonance has shifted down very slightly. If we now have a look at these various frequencies, let's see, we would so before we were oscillating at this point here with the vacuum tube oscillator, which was about Mark II is about 1.75, 1.76 when the tuning capacitor for the primary was fully wound in. So if we now also go and have a look at that phase change, 3, now we find it very interesting. That is also right on a serial resonant point. And interestingly enough, it's 2.58 megahertz. Very, very close to where the predominant oscillation frequency, or where of all the frequencies going into the system from the spark gap generator, when an average is taken of all of those, the predominant frequency that comes out of that, as shown on the universal counter, was around about that frequency. So in other words, that serial point represents, which is largely defined by the transmitter, those oscillating currents, is where the ring down is taking place. So in other words, that secondary is ringing down and it's ringing down at that frequency, predominantly at that frequency, and that's what's being measured predominantly in the primary circuit. Of the transmitter. So what we're going to do now is, I'm just going to stop that. We're going to take a more detailed look. So if I reduce that to 5 megahertz, let's sweep again. Okay, so now we see that whole area from 100 kilohertz to 5 megahertz in much more detail. Got those 3 resonant circuits in there. And I'm going to wind back to the balance point. So I'm going to wind out the primary now until we get back to the point where those upper and lower frequency points, the magnitude of those impedances, are balanced. Remember, that's the effect of the primary and the secondary interacting. So the phase change from the parallel primary circuit is now off the top of the screen. It disappeared off as we were adjusting, and we're just about at the balance point there. Very high Q, very sharp interaction going on there. I'm going to reconnect the transmitter and the receiver via the single wire. Okay, much as we saw before, so now we've introduced those 2 other resonant circuits. So there's an interaction going on here as here. We've got those double peaks. Again, we're going to retune. Winding the tuning capacitor in until we get to about there. So there we're about balanced between the two. Probably around about 800 to 850 picofarads. Again, this hasn't really changed, well, not very much at all. It's represented by the tank circuits in the primary. Let's have a little look at this serial point. So about 1.09 for the tank circuit. About 2.4, that's central resonance. Again, the lower bands, there we are. 2's 1.95. That was a very interesting point when we were driving it as a linear oscillator. This lower band 1.82, and for the upper frequencies it's 2.8, and the upper one, which was the other stable point for the linear oscillator, is about 2.96 megahertz. Put that back in the center. Now if I connect the load at the end again, so attached to the primary of the receiver, then we have reduced the Q by putting that load in, and then we'll rebalance up. Go back to the balance point, which is a slight shift there. So again, very similar characteristics as we had expected from the first part. We also now have this here. If I take out the tank capacitors, we will see that disappear. I'll just pause for a second. taken out the tank capacitors. We'll rescan that, and we see this phase change has gone. Slight shift of the other points as well, because of the interaction effect of that peak. So now there is a balance one can consider. Well, why isn't the tank capacitor resonant circuit arranged to be at the same resonant frequency as the secondary? Now there is a balance between here, between coupling as much energy between the primary and secondary as possible. That's based upon obviously matched frequency resonant circuits, but also the amount of energy that's stored on the tank capacitor. Because when the spark gap fires, in effect there is a short circuit or very, very low impedance across the spark gap. The two tank capacitors become joined together at their ends, and they discharge through the primary circuit, or they ring down, causing that burst that we saw on the oscilloscope in the secondary. And the same is very similar in the primary, and you see predominantly those two frequencies going on in that burst. So you see some of that oscillation that we saw in the burst is a result of the oscillations in the primary circuit. Further on, those oscillations are as a result of the oscillations in the secondary. So as the energy is used up in the primary, so with the high Q system, which this is, then the oscillations continue in the secondary, and you see those two distinct frequencies. You see the resonant frequency of the primary, and you see the resonant frequency of the secondary. Now, if I just put the tank back in, okay, so I've put the tank back in. Now you can see these are a result of the tank capacitors in the primary. If I was to reduce those tank capacitors further, obviously this phase line would start moving up in this direction, and we would start to get a closer match between the tank circuit, the primary tank circuit, and the secondary of the TNT transmitter. Now there is an optimum point, because the disadvantage of reducing it, of the capacitance, is that there's less energy stored per cycle. So there is a balance between the amount of energy stored on the tank capacitor and the resonant frequency that the tank circuit presents in relation to the resonant circuit of the secondary coil. Now, in this system, what it's set to now, so about a total tank capacitance of about 2.3, 2.4 nanofarads, appears to be around about the optimum point. It can be adjusted a little bit around, but it changes very little the amount of energy, and hence that's coupled to the secondary, and hence power that's actually dissipated or transferred in the TNT transmission system. Okay, so really that concludes looking at the small signal AC analysis now. Now we're going to have a look more at the running of the system and what's going on in the experimental area. Then also we're going to have a look at what power, if any, can actually be transferred to the load at the output of the receiver. Okay, so now we're going to have a look at the actual experiment running itself. I've reconnected the generator, removed the vector network analyzer, and now I'm just going to run again. So it's about 300 watts. as before, 4 amps primary current and around about 150 amps. There's probably a fair bit of tension on here. Yeah, there is discharges coming out of the top there. We see though that given I've got the capacitor almost fully wound in at the moment, and all of the power currently is being dissipated in the single wire load. So what I'm going to do now is I'm actually going to tune all the way, so that's fully in, I'm going to tune all the way steadily up. See the tuning there makes not that much difference now. Now it's falling off a bit. All the way up. That's fully wound open. Now wind it back down again. You see the load, the single wire load remains lit all the time across the entire tuning range. And that is a reflection. It's brightest at the bottom here, but that is now a reflection of the fact that we have we have very broadband frequencies here. So because of all those bursts and the pulses going on in the spark gap and single wire system, we have a very wide broadband range of frequencies. So therefore, even as I tune the coil, there is always frequencies there to be coupled. We are not changing the oscillation frequency of the generator as we were with the linear oscillator. We are now simply pumping out a very broad range of frequencies. Some of that energy is being coupled into TNT transmitter, and that power is being dissipated in the single wire load. We can see that it's the high tension is illuminated here, but at the receiver there isn't really any tension at the top. Here, a little tiny bit, even if I put my finger to there, there's a very little tiny bit appears. So really, all of that energy is being dissipated there. And if I pull that out, yeah, it just continues just the same as before. So it's being dissipated in that single wire load. Obviously, I'm improving the cavity. When I plug that back in, when I take that out, going back to part 1 of transference of electric power, obviously we've just got an open circuit there. We do have a cavity established, and we can see the various dissipation according to the longitudinal mode that's in there. Plug that back in. Obviously the cavity is similar at each end. There's obviously an imbalance here. As you see, it's somewhat brighter than it is in the middle. But tuning, the important thing here is that tuning makes very little difference at the primary capacitor. So I'm just going to do that again. Fully wound in, winding out. So that's 300 watts. All the way open. Again, close it all the way back down. So that's now fully closed. We'll just turn off for a moment, give the transformers a chance to cool down a little. Okay, what we've done now is we've focused on very in that central region where the load is single wire load. We have just actually removed the receiver from here. This is the receiver fly lead. So we're just operating the cavity between the TNT transmitter and the open circuit, and we're going to show that nice effect from Tesla's radiant energy and matter. This is just a very quick preliminary look at this, where we see where we can actually draw various materials, usually conducting materials, towards the pressure wave in the single wire, which actually gets irradiated off of the filament of the bulb. So if I just start now, we turned up the power a little bit to about 500 watts. We're using a single bulb there, so we can see the effect very, very clearly. Let's just turn it on. It now touches off. Off. On. Okay, so that shows that's an aluminium foil on a masking tape, and when we start the circuit, there's around about a 4-5mm gap between the aluminium and the bulb surface. When we turn it on, you can hear the aggressiveness of the spark gap in the background, which is that was around about between 600 watts. And we see that that unusual effect of the metal being pulled towards the surface of the bulb, and that's quite works quite commonly with the metals. That's an aluminium. We've got copper there, and you can also put a leaf there, and interestingly enough, it is significantly affected also by the biofield that's around there. So if I turn down the power a little bit and turn it back on, and then introduce my hands there, you see it pulls very hard. Here we go. There. Let it off. Pulls very hard. We can even move it further away. Quite a bit, much bigger gap there. The other part also is to feel whether we can feel that pressure wave, and we just turn the power down a little bit, say that's about 400 watts, and we put our fingers near, being careful not to touch the metal of the bulb. You can feel, I can feel the vibration coming off on my fingers, as per the very famous experiment that was, of course, done by Eric Dollard and Peter Lindemann and Tom Brown, where they demonstrated this very neatly. Now you can also see here is a very interesting, is the filament is actually responding to that vibration. As you can see on the camera, as I put my fingers near, the filament is actually moving. It's vibrating. A pressure wave is being exerted on the filament. Very difficult to see. Sure, easy to see here, but not sure how that will come out on the camera. I can still feel those vibrations coming off. If I just turn the light off in the lab, we'll be able to see that more clearly. So I've just turned the light off. I'm going to turn right down so we just see the filament lit there. We're only running at 33 watts. Not enough power. Go up a little bit more. More. Now we can't see the filaments. Very difficult to see that on the camera, but the filament's actually vibrating. I can feel the vibrations coming off the bulb. And the filaments are just moving as I move my fingers around. Let's go back to normal power. So go up to about 300 watts. Turn the light back on again. Let's put this back. And again, it pulls it towards it. More gap. Too far away, but if I bring my hand in, it's going to pull it very, very well. There, I never even touched the bulb, it only came near. There. Again, we can see that moving in. So it definitely has an interaction or reflection from that biosurface of my hand. Now it has been claimed that eddy currents is the source of this, although I don't think that's actually the case. It's more to do with the longitudinal mode, the pressure wave between the electric and the magnetic fields of induction, and we're just going to see that now. We're going to bring that very close. Now I'm going to bring a magnet right up. It makes no difference. It's a magnet on the end. It makes any difference on this side. I can't affect that. That's a magnet attached to a nylon stick, and it makes no difference. Even if I try to touch it and pull it away, it doesn't have any effect. When I turn that off, now it's released it. So the magnet really didn't have any real impact on that, and it doesn't actually even pull it to it. So doesn't make really any difference. Oh, now it's pulled it too. I just put the plastic end in. Nothing. But if I bring my hand in, straight away. Time. See the gap there between the two. Up the power a bit. Oh, just need to adjust the spark gaps a little. Okay, adjusted the spark gaps again. They were getting a little bit too closed. Oh, just adjust them again. Once more, there, immediately pulls, turn it off, releases. Immediately pulls. Immediately pulls. So that's a preliminary demonstration of Tesla's radiant energy and matter. We're going to do more on that, much more. Now the effect is quite small here, so really, it's only really grabbing that piece of aluminium foil over about 4 or 5 millimeters away from the bulb surface, and the filament is in itself around about 8 to 10 millimeters away from the surface of the bulb. So we are seeing that effect there because of the longitudinal pressure wave that arises again because of that unusual interaction between the electric and magnetic field that is very characteristic of the cavity formed in the TMT between the top load and the boundary condition at the other end of the cavity. Now, it's possible to make that much stronger so that the coupling of energy for the TMT is relatively low. So we can see that the primary and the secondary are loosely coupled here, and even driven by the spark gap generator quite powerfully, the effect on the strength in terms of pulling that aluminium foil, or the force applied to it, is relatively low. So you can only really pull it over a small distance. If we were to increase the coupling, and we use in other words, increase the power of the cavity, then we could see that and increase the tension as well, because we only have 2 turns here to 20 turns on the secondary, so 2 turns in the primary, 20 turns in the secondary, so a magnification ratio of 10. So the tension is relatively low. Now that's good for the transference of electric power experiments and everything like that, but for some of the radiant energy and matter experiments, then it's much preferable to have higher tension. But you still need that longitudinal mode, that longitudinal pressure wave that's formed between the electric and magnetic fields of induction in this kind of system. And even better, of course, would be to be able to start to use impulse currents. So at the moment we're using the spark gap, we're getting a burst of energy, very much a pulse of energy every half cycle of the line frequency, which is 50 hertz, so we're getting 100, the spark gap is firing 100 times a second. And we are just allowing that to oscillate. So oscillating currents in the primary generate oscillating currents in the secondary, and the overall effect of that is you do see this radiant energy and matter effect, but in a way, because that pressure wave results very much from the impulse nature of how it's driven. When we allow those oscillating bursts to continue over a period of time, it really just ends up weakening that wavefront. So what we actually have to do is, if we were able to trigger that impulse at the moment that the spark gap starts to fire, and then cut it off very quickly, then we've got a very strong initial impulse current, and coupled to the secondary, that's a big impact. It's the shock wave of the front is strong, and then we would see that that effect very much amplified, not only in what it's able to, the forces it's able to exert, but also the distance at which it's able to exert itself. And it's that we're going to be looking at later in another experimental video, which goes much more into looking at the rather than the transference of electric power. It starts looking at Tesla's radiant energy and matter experiments, where we actually use the diathermy replica, which has got a tightly wound secondary in there, and we can get much stronger impulse effects but we'll be looking at that subsequently. So from here, we also need to have a look at what is going on at the receiver load. So far, we've looked in the cavity, we've looked at the single wire, all the power being dissipated in the single wire, and I can say, throughout what we were doing there was only a tiny glow at certain points of the tuning in the receiver. So before, when we were looking at the vacuum tube generator, we were able to find a narrow tuning band where we could light that load fully. We had 50 watts at the output of the receiver, and around about 1.92 to 2.05 megahertz, we were able to light that load fully, and the power dissipated in the single wire load was very low. So we haven't been able to accomplish that with the spark gap generator so far. So we're going to take a look at that now, but if we think about all of that energy from the spark gap spread out in the broad band, and there is only a very narrow tuning range of frequencies with which we can actually transfer electric power from the generator in a very low loss to the final receiver load. So in a way, we're only coupling a small amount of energy that is being stored in the transmitter tank capacitors. Just a small amount of that energy is ever going to reach the load on the output of the receiver, and hence that's why they just don't light very brightly. We also, because we've got all that energy being dissipated in the single wire, then we are essentially also we're just dissipating the power there, not transmitting it into the final load, and that is in effect actually a great disadvantage of using a spark gap generator in this kind of transference of electric power. We can't get all the power into a narrow frequency and send that from the generator to the receiver in the same way that we can with the vacuum tube oscillator and in the linear amplifier situation. So next we're going to have a look at what we can get into the load. I'm just going to move the camera and to the receiver, and then we'll take a look from there. Okay, so now we're looking at close up of the load of the receiver. So this is the output of the primary of the receiver. We have two bulbs of this load connected. So it's a 50 watt load. These two are not connected as before. We're simply taking the output through in parallel out from the secondary through to the primary of the receiver, tuning capacitor in parallel, and then the load. And we also have the ground connection here. That's a large many core cable that goes down to RF earth. We have that connected on this side as well. So now we have tuned the transmitter, the vacuum variable capacitor, so the primary tuning capacitor at the transmitter. We have tuned that to the optimum point for transmission of power. We're running the generator. We're going to run a generator at 400 watts, and we have the load in the single wire is still connected. So when I turn it on, the load lights in the single wire, and we can see that the filaments here are just lit. Now what I'm going to do is I'm going to change the tuning capacitor in the transmitter over its full range, and we see what happens there. So that is capacitor fully wound open, and really no power transferred, or very, very little. We can't discern it in the bulb. Gradually winding the capacitor in, there we are. Now we can see more power being dissipated, and fully closed. And really, again, no power when it's fully closed either. So we go back to that optimum point, and about there, seems to be the optimum point. And again, we've just got the glow back just in these two bulbs, but hardly any power transferred at all over the full tuning range of the primary capacitor. Meanwhile, the load in the single wire was lit all of the time, as demonstrated previously. So really, that again, just going over that broadband energy created by the spark gap generator, coupled into the TMT transmitter, and essentially almost all of it dissipated in the single wire load. Very little of it ends up with not been easily been able to tune these two together to create a good strong cavity there to establish an LMD standing wave, so we can get to our low loss transmission condition when both transmitter and receiver TMT are optimally tuned for the transverse mode in interaction with the standing wave for the longitudinal mode, and then we can get maximum power transferred into the receiver load. We haven't been able to create that condition in this setup. So what I'm going to do is to try to assist getting more power into the receiver load. I'm going to remove the single wire load. So I'm going to take the bulbs out, just short the wire together. So it is a single wire just between the transmitter TMT and the receiver. So now we try to dissipate as little power as possible in the single wire, and we see what we get at the receiver. Okay, so it looks better now. Still not a large proportion when you think, although the cavity is now better, there's tension at the receiver top end and the transmitter top end, and the load bulbs are lit, and we are putting in, well, almost 500 watts. I mean, that's 500 watts, and I would say that the 50 watt load is lit about 1/3. So probably not much more than 15-20 watts in the receiver, yet we're putting 500 watts into the input of the high voltage transformers. Not a very good transmission ratio, for sure. But then so little of that energy is actually really getting through. I'll just adjust the spark gaps again, and then we'll try tuning and see whether we can improve any of that. So tuning at the transmitter. So we run again, back to the same point. I'm just going to change the tuning. So that is fully open, 20 picofarads, closing, 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 very little difference. There, that's about the brightest point. That's again back to our optimum position, fully closed. And that's dimming off again, hardly any power transferred. Back to our optimum position, about there, just readjust the spark gaps a little. Just put it on. So really that is about the optimum position. So in that situation, we have the two. Maybe I'll just turn the lights off. Okay, so we have the two transmission coils. The transmitter TMT and the receiver TMT. They are tuned at the optimum point, like before, like we did with the linear oscillator. There is a high tension at the top end of both of the coils, but there's still very little power transferred because the spark gap is only creating or generating a small proportion of energy in the band that is actually being transmitted through this high Q system. So with this kind of generator, we are never going to get lots of energy from the generator to the receiver based on this, because there is so much energy which is lost, in other words, is not transferred between generator and receiver, but is basically just incompatible with the resonant frequency of the system. So that is transference of electric power and a little bit of Tesla's radiant energy and matter when using a spark gap generator to drive a TNT system.